In our last video for this unit, we're going to look at how to write recursive and explicit equations for both arithmetic and geometric sequence problems and series problems. And we're also going to be spending today, doing some mixed practice problems over everything, because I know we've thrown a lot of material at you the last couple lessons, and you need time to kind of process and practice. So I'm actually going to split this into two videos. So the first one is going to look at our writing recursive and explicit equations and a couple more word problem examples. And then the second piece is going to be some extra mixed practice problems. So if you're feeling pretty comfortable on these, focus just on the first video. But if you find you need another explanation on some of these problems, definitely watch the second video that I'll have posted right underneath this one. So let's start out by looking at our formulas. Now, I didn't use every single formula that you see on your formula sheet. So today we're looking at all of them. And so again, this is kind of spreading them out, but these are the 8 formulas that you're going to have available on your formula sheet. Now, the difference is I've added in one extra formula for both the arithmetic sequences and series and the geometric sequences and series. But all the variables are still the same. So n still means, what number term you're at. A sub n, you're figuring out what the value of a specific term is. And then S sub n, what's the sum of the series going up to that number of terms, or S sub infinity, like the bottom right, where you're looking at the sum of the entire geometric series. Again, you can only do that with a geometric series. If you're doing this with an arithmetic, don't forget, those are all the ones where you're adding or subtracting. So you're always going to have that same difference kind of added on or subtracted on. And so you're never going to have a, specific value that your sequence or series, that your series adds up to for arithmetic, because it's never going to, decrease down like those geometric series can. So when can you use each one? Because we really kind of focused on one specific type each of our previous 2 lessons, and you're looking at everything in this one. So our first equation in both of these. So first line on the arithmetic, a sub n equals a sub 1 plus n minus 1 times d. And for geometric, a sub n equals a sub 1 r raised to the n minus 1. Both of these, you're just starting with the first term, and then it's explaining kind of your rule that you're going to apply. And so you could use this to find any specific term very easily by just plugging in what you know for n and what you know the pattern is. So this is what we would call an explicit formula. So this is explicit, where you know a sub 1 and n. So those are known. However, the next formula down under there, and this is the new one that we haven't had in our 10.2 or 10.3 examples. So this is what we call a recursive formula. So let me write that down. Recursive formula. And so the difference with the previous one is, you'll notice I have this term a sub n minus 1. So if we have like a sub 3 versus like n minus 1, so take 1 off your n, so a sub 2, pretty much what these formulas are looking at are, if I want to know this particular term, then here's how I get it from the previous one. And so we want to be very careful with that. We need to know exactly what the previous term is to even use these formulas. So when we were doing problems where we were saying, oh, well, let's just add to get to the next term, or let's multiply to get to the next term, technically we were doing a recursive formula because we were just paying attention to what was that previous value, and I'm just going to build from there. So this is always going to be based on previous term. So most of the time when I'm doing these problems, if I can, I'm going to use that explicit formula, because I don't need to know necessarily the previous term for each one. I just need to know the first term and what's the pattern. Okay, and then our last 2, again, just as a review, if we're going to do a sum of a complete or a, or a set series, where we know every single one of the terms and we're not kind of extrapolating the pattern with this one, and this one, that's when we're going to know. So if I know that my series has 10 terms and I want to find the sum, those are the formulas that I could use. Again, our 2 different versions for arithmetic, just depends on the info that's given. But for geometric, we would have to use that first S sub n formula if we're just looking for a specific sum of a specific set of terms. Where if we're looking for an infinite series, so infinite series, that's the only time we're going to use that S sub infinity formula. And we can only use that when the terms get smaller and smaller and smaller and eventually go down to 0, so we can find a distinct sum of the whole entire series, no matter, where we cut it off. Alrighty, so some sample problems, a couple word problems, and then again, the second piece of this, you can watch the video if you need the extra run through some extra examples. Here we go. Example 1, write an explicit formula that could be used to find the nth term. So explicit formula, first we notice, hey, this is an arithmetic sequence. So if I go back up to that table, arithmetic for the explicit, the first line, that's a sub n equals a sub 1 plus n minus 1 times d. Alrighty, so nth term means I'm going to be plugging in the n value. So really what I need to figure out is what's my a sub 1 and what's my d, my common difference. Alrighty, well, common difference, how do I go from 2 to 5? And then 5 to 8, and then 8 to 12? Well, all I need to do is add 3. So my common difference is going to be 3. And what's the first term in the sequence? Well, that's just 2. So if I rewrite that formula, a sub n equals 2 plus n minus 1 times d, which is 3. Now I could leave it as is, or I could write this out. And so let's go ahead and multiply out that 3 and see what we get. So we would get, let's see, distribute out the 3, we would get a 3n minus 3. And so then ultimately when we simplify that out, we're going to get a sub n equals, let's see, 2 minus 3 would give us a negative 1 plus 3n. And again, either this or this one technically would be valid answers, but you'll notice that last one kind of looks like the way they plug it in with that summation notation. So you don't have quite so many terms to have to worry about. Alrighty, example 2. Write a recursive formula that describes the arithmetic sequence. So this is actually easier than you think. As soon as I see the word recursive, really I'm just thinking, what's the rule? And I know it's arithmetic, so I know I need to add or subtract. I just need to know what my common difference is. Technically, the formula is a sub n equals a sub n minus 1 plus d. So if we know the previous term, all we need to do is figure out what's that common difference. So how do I get from 6 to negative 2, and then from negative 2 to positive 2, 2 to 6, 6 to 10? Again, arithmetic means I'm adding or subtracting. Well, to get from 2 to 6 or 6 to 10, those are pretty recognizable as just add 4. So test it with the first few. Negative 6 plus 4 gives me negative 2. That one works. So I know my d equals a positive 4. So that means my recursive formula is just a sub n equals a sub n minus 1 plus 4. That's it. For arithmetic, all we need to know is what's that common difference. Alrighty, so let's do an application problem for arithmetic. So, word problem. So suppose on January 1st, you deposit $1 in your piggy bank, and then on January 8th, a week later, you deposit $1.50. So 50% more, or 50 cents more. January 15th, you deposit $2. And each week thereafter, you deposit 50 cents more. So how do we know that this is an arithmetic sequence? Are you multiplying or are you adding? Well, we are adding 50 cents each week to our total. So not for the total sum, but total what you're putting in each week. So first week is 1, next week is 150, next week is 2, then 250, then 3, and we'd keep up with that pattern. So it's still just adding 50 cents to get the next amount that you're going to deposit. So what would we deposit the 52nd week? Well, what do you think, explicit or recursive? Well, recursive just means I've got to calculate each one of those. So we're going to use the explicit formula. So a sub 50 equals a sub 1 plus n minus 1 times d. Okay, so first week you deposited $1. 52nd week, that means 52 equals your n, so 52 minus 1. And your common difference, what are you adding on extra? Is the 50 cents, so 0.50. So let's just calculate that out. Alrighty, so we have 1 plus 51 times 0.5 or 50 cents. Alrighty, so that equals 1 plus, so 51 times 0.5 is going to give me 25.5. So on the 52nd week, we're going to deposit $26.50. That's just how much we're going to deposit. But part C, what's the total that's actually going to be in the piggy bank? So if we're going to total everything up that you deposited all 52 weeks, then you're actually finding the sum. So that means we need to find S of 52. And so look back at your formulas. So we have two versions that we could use. We could use the first one a little shorter, n over 2 times a sub 1 plus a sub n. Do we know our first and our last deposits? Well, then let's use that one. So again, we're going to do n minus 2 over a sub 1 plus a sub n. And we already figured out a sub n in that last part. So 52 over 2 times, first deposit was $1, last deposit was $26.50. Alrighty, so again, go ahead and do your parentheses first, and I'm going to go ahead and do the decimal for the front half. 52 divided by 2 actually doesn't even come out to a decimal, it's 26. And then adding the 1 onto your 26.50, 27.50, multiply those out, you will have $715. So small increases can make a difference in the end. Alrighty, so now let's do the same thing and look at some geometric series and sequence problems. Here we go. So example 4, write a recursive formula that describes the geometric sequence. So geometric means we're going to multiply something over and over again. But recursive, again, your recursive formula, to go back to the formula that we have, well, that's just a sub n equals a sub n minus 1 times your r. You're just stating basically the rule. What do you have to keep multiplying by each step? So what do you multiply -4 by to make -8, and then -16, and then -32? If all the signs stay the same, then you're just multiplying by 2. So if your r is equal to 2, then that means your recursive formula is just a sub n equals a sub n minus 1 times 2. That's it. Slightly longer formula for the next one, because now we're looking at the explicit formula. So that means, again, for a geometric sequence, we're going to be looking at a sub n equals a sub 1 times r raised to the n minus 1. And again, keep in mind that first term, we're not actually multiplying, we're just starting that first term. That's why we have that n minus 1 up in the exponent. So what do we multiply 325 by to get 65? We got to do a little bit of math here. So I'm actually going to go ahead and divide. Let's always go with the second term. So let's do 65 divided by 325. And you'll see why I'm doing this in a second. So 65 divided by 325, I'm getting out 0.2. So 0.2, or we could think of that as 1/5. So if I multiply by a number that's smaller than 1, what's going to happen to that resultant answer? And it's going to get smaller. So really, that's what we're doing. We're dividing by 5 or multiplying by 1/5 as our r value. So that's our r. So that's what I'm going to plug in. So a sub n equals, our starting value a sub 1 was 325, and we're going to multiply that times 1/5 raised to the n minus 1. Again, we can't go any further than that. We've got that exponent of n minus 1 on the 1/5, so I cannot combine the 1/5 with the 325. You almost have to think of them as separate factors. They can't kind of mingle together when you've got that exponent in there. Alrighty, let's do a word problem on here. Here we go. Number 6, a super ball is dropped from a height of 2 meters and bounces 90% of its original height on each bounce. So how high off the floor is the ball at the top of the 8th bounce? So if you've ever bounced one of these things, if you drop it, so you're not throwing it down, you're just dropping it from a height, it's not going to bounce back up to that height where you dropped it from. It's going to be a little bit lower and then a little bit lower and then a little bit lower, and eventually it'll be down to the end because it's losing its energy. It can't bounce back up. And so we can think of this 90%. Well, that's to find 90% of something. What are we going to multiply by? Okay, what's 90% as a decimal? Yeah, move your decimal place over 2 places, so 0.9. So if I want to find 90% of something, I'm going to multiply it by 0.9. Okay, original height is 2 meters. So we know of our info. So at the 8th bounce, we're looking for what a sub n is. If a sub 1 times r n minus 1, what can we fill in? Well, we know that 0.9, that's our multiplier, so that's our r. Our a sub 1, our first term, our first value, that's the height that we drop it from. So that's a sub 1 in this scenario. So fill those in. For the 8th bounce, that means what is our n value? Well, that's going to be n equals 8. So let's fill that all in. So here we go. So a sub 8 equals 2 times 0.9 raised to the 8 minus 1. Simplify it out. So 2 times 0.9 raised to the 7. So you're going to want to simplify that out first. 0.9 raised to the 7, we get kind of a long decimal, 4, 7, 8, 2, 9, 6, 9. Whenever possible, again, I would use the entire value. So if you're on a TI calculator that you're kind of doing this in stages, just use that previous answer, just hit times 2, and it'll automatically multiply it by the full answer. You don't have to type the whole thing in. And we should end up with approximately, I'm going to round off this final answer, 0.96 meters. So at the end of 8 bounces is a little less than, we're reaching a little less than half the height. So that was a very bouncy super ball. Alrighty, so we've got a bunch of practice problems on here for you to do. Again, if you're feeling pretty comfortable on these things, I would go ahead and try out the practice that we have for this lesson. But if you feel like you need a little bit more guidance, you need to go through and try out some more examples. Again, definitely watch the second video I have posted to see me run through the extra examples that I have in the organizer.